Welcome students. In this question we are going to learn how to solve this problem, log 8 to the base negative 7. Now most times in your classes you would have been told that log of negative base, or I should say log with a negative base, cannot exist, right? So they would have told you this. Now on the other end, if someone were to ask you this question, can you solve this log 8 to the base of negative 7? If you would have been given this fact, you would have immediately said no, this is not possible because the base of this logarithmic function is negative 7. Now the information or the fact that you've been told that log with a negative base is not solvable is in fact a fact, or I would say is indeed true. Now why is it true? I should say it is both true and false. Now why is it so? Because the domain that we are considering here is all real numbers. That is the major problem. So if your domain is going to be all real numbers, then this is not solvable. But if you are going to extend the domain a little bit and include complex numbers, then this question is solvable. So having mentioned that, if someone were to ask you, is log 8 to the base negative 7, is it solvable? Yes or no, then immediately your question should be, what is the domain that is being considered? If they say real numbers, then your answer should be no. But if they say complex numbers, then your answer should be yes. So having mentioned that point, let me just shed some light about the different forms of logarithms that we have studied. Now there are major difference, or I would say two main logarithms that are being taught. One is called as common logarithm and the other is called as natural logarithm. Now what exactly is the common logarithm? Now common logarithms are nothing but logarithm to the base 10. So in other words, they are nothing but inverses, or I would say inverse of 10 raised to the power x. Now coming to the natural logarithm, what are those? They are represented by ln and they are actually base e logarithms. And what are these base e logarithms? They are actually inverse of e raised to the power x. Now where do we find applications of common logarithm? In most of the times in scientific problems or when dealing with scientific notation. That is when you will be using common logarithms. Now where do we use natural logarithm? Whenever you are dealing with calculus and in algebra. So you would have popularly seen differentiation of e raised to the power x, which is a very important concept in calculus. And also in complex numbers, e raised to the power I theta, you would have come across that this is basically a complex number of the form cos theta positive I sin theta, right? We are going to talk about this later. So having mentioned these two different types of logarithms, it is imperative to mention here that the base for common logarithm can be any complete number or any whole number. Most of the times we either use the base to be as 10 or the base to be as 2. But this particular number can be any positive number. Of course, there are certain conditions for which this base is made a choice, which we will see later. But just for the scope of this problem, I would just make a mention that most of the times we would be, or a student would be exposed to either base 10 or to base 2. But in no way he or she would be exposed to a negative base. Negative base is a no, not possible. So having mentioned that, let us move on. Now, in logarithms, it is important to know this formula, what is called as change of base. Change of base formula. Now, what is the meaning of this formula? Now, suppose you are given a problem, say log a to the base b. I can always rewrite this by introducing a new base. Now, say for example, I want to introduce a new base called c. I can rewrite log a to the base b as log a to the base c divided by log b to the base c. Now, you have to observe here that the base is now literally is being featured as a quantity on which a logarithmic function is operated on. So that is the power of the base formula. Now, having obtained or understood the base formula, we can go a step further. In other words, if I were given log a to the base b, I can literally use a base e, that is, change a common logarithm into a natural logarithm using the base change of base formula. So how do I do this? I can rewrite log a to the base b as ln of a to the base e divided by ln of b to the base e. So this is how I do it. So now we have been given this question, that is, evaluate log of 8 to the base 7. I can rewrite this as ln of 8 to the base e divided by ln of negative 7 to the base e. So this is always possible. So now, having got this, I am going to use the log of product rule, that is, log of ab is equal to log of a positive log of b. Of course, since I am using ln, this formula is also applicable to ln of ab being equal to ln of a positive ln of b. It's possible. So what I'm going to do, I'm going to rewrite this as ln of 8. I'm not going to specify the base because it's going to be e. So this is going to be ln of negative 7. I'm going to rewrite that as positive 7 multiplied with negative 1. Now this is going to be ln of AB formula. So this is rewritten as ln of 8 for the numerator divided by ln of 7 positive of ln of negative 1. So this is possible. We can find this value out, right? Ln of 7 is easy to obtain. Similarly, ln of 8 is easy to obtain. Now the question comes, how are we to obtain ln of negative 1? Okay, now this is where complex number comes in handy. Now, if you remember, I mentioned that if our domain is complex numbers, then we can always find the value of log of 8 to the base 7. So that is what I'm coming at now. Now, we have to obtain the value of ln of negative 1. So how are we going to do that? Now, you have to know that any complex number is represented as z is equal to x positive iy. Now, if I were to take a complex number z to be as negative 1, then this negative 1 can be represented as, say, negative 1 positive 0 times I, where the real part is negative 1, imaginary part is 0. So I can very well do that. Now, having mentioned this, it is also imperative to understand that any coordinate, any point in the xy coordinate can be represented in polar form. Now, what exactly does it mean? It means, all I'm saying is, if I'm given a coordinate in the xy, I can also have another representation. Okay, this is a two-dimensional representation, and that representation is actually given by what is called as polar form. Now, let me give you a slight introduction to polar form. Now, I got a point, say x comma y. So this is the point. Now, the same point, this is the x-axis, capital X-axis, capital Y-axis, and x comma y is a coordinate. Now, this same coordinate can be represented by r comma theta. Now what exactly r comma theta? Now r is the magnitude of this point from the origin, and theta is the angle in which this particular line is away from this standard line. So when I say standard line, we are talking about this x-axis. So any coordinate, any point for that matter, now say in this case I am taking z to be equal to -1. Now this -1 is actually nothing but as a coordinate -1 comma 0. Now that -1 comma 0 is going to be somewhere over here. Okay, so this is -1 comma 0. This point is -1 comma 0. Now you have to understand that for this point I have a representation, and that representation is given as the following. Now as I mentioned to you, a complex number is of the form x positive iy, and this x positive iy is represented as r times e raised to the power I theta, where r is a magnitude, and I can very well represent e power I theta as cos theta positive I times sin theta. Now it gets interesting here. Now x as a coordinate r times cos theta, and y as a coordinate system as r times sin theta. So any given point x and y, this is coming all the way from calculus, right? We use it as a definition. Now any x can be represented as r times cos theta, and any y can be represented as r times sin theta. Now it is enough that we have this definition just to make just to understand that a coordinate can be represented in this fashion. Okay, now we are being given this point -1 comma 0. Now what is this -1 comma 0? This -1 comma 0 is nothing but r times e power I theta. So how do I make the representation? I represent z to be as -1, which is equal to -1 positive 0 times I. So I need to have a r there. Now for sure, clearly I know that r should be equal to 1 here, because that is the magnitude of this particular coordinate, -1. So in this case it's going to be 1 times cos theta positive I times sin theta. Now when exactly left hand side, or I would say when exactly this coordinate or this component will be equal to -1, when is it possible? The only value for which this is going to be true, theta should be equal to pi. When theta is equal to pi, this is equal to 1 time of cos pi positive I times sin pi, which is nothing but equal to -1, right? Now you have to understand that if I am moving from here to here, which is -1 here, right, the value of theta is going to be pi. But what if I were to move all the way down and then reach here? So that means I am making multiple turns, right? So the idea what I am trying to emphasize here is this representation of z is equal to -1 is equal to e raised to the power I times theta can be extended. So how do we extend it? We can extend this to be as e raised to the power. In this case theta is going to be pi, and we can have multiple rotations, right? So that is going to be 2 times k. In fact you can use k or n or anything for that matter, because the k that we are going to be talking is going to be element of integers. Now when k is equal to 0, we are getting e raised to the power I pi. So that is nothing but this quantity. This is nothing but e raised to the power I pi, which is -1. So when k is equal to 0, I get -1 is equal to e raised to the power I pi. When k is equal to 1, I get -1 is equal to e raised to the power 3, or I times 3 pi. So I times 3 pi, my pi is going to be 180. If I'm going to multiply by 3, this is going to be 0, 24, 2, and this is going to be 540. So 540 means one complete rotation from here to here is 360 plus 180. So that is exactly what I was talking to you about. So this is going to be producing me all values. So which I should rewrite this. So z being equal to -1 can be produced by e raised to the power I pi of 2k positive 1. So I have a representation for -1 in form of complex numbers. So having obtained this, let us go back to the problem. So in this question, what I'm going to do, I'm going to rewrite this to be equal to ln of 8 divided by ln of 7. In place of -1, it's going to be ln of e raised to the power I pi of 2k positive 1. So this is going to be the case. Now you have to understand that ln of e raised to the power x is nothing but x. So this value can be rewritten as ln of 8 divided by ln of 7 positive I times pi of 2k positive 1, where k is an integer, element of integer. So this is going to be the solution. Now we can extend this to something more interesting. So how do I do that? So I'm going to give you this interesting deduction. So let's see that deduction. Now imagine you've been asked this question. Evaluate, say, log of e to the base -1. So how do we do that? So this, I'm going to rewrite this as, say, ln, I'm going to introduce a new base called e. So this is going to be ln e to the base e divided by ln of -1 to the base e. I don't need to specify this, but still it's okay. Now this is equal to ln e to the base e is going to, this is going to be 1 over, I get ln of -1. So ln of -1. So when do we produce ln of -1? So we need to have -1. So imagine I'm taking -1 over here. So -1 is equal to e raised to the power I pi of 2k plus 1, right? So to get this value -1, I have to have the value of k to be equal to 0. So when k is equal to 0, what happens? I get e raised to the power I pi. So this is going to be producing me -1. So in place of -1, what I'm going to do, I'm going to be substituting ln of e raised to the power I pi, right? But we know that ln of e raised to the power x is equal to x. We know this. So this is equal to 1 over I times pi. Now on the left, I've got log e to the base 1. If you're not interested in having this I in the denominator, what you can do is you can multiply by I and divide by I. So this is going to give me I divided by I squared times pi. I squared from complex number is -1. It has got a value of -1. So this is going to be I divided by -1 times pi. I can rewrite this as -I divided by pi. On the left, I've got log of e, the base is -1. Now what I'm going to do, I'm going to move the pi that side. So this is going to be pi is equal to -I. Now I'm going to push this log e to the base -1 down. So this is going to give me log of e to the base of -1. Now if someone were to ask you what is the value of pi, clearly you can say the value of pi is -I divided by log of e to the base -1. Of course, they're going to ask you the next question: how did you arrive at this particular value? And then you can show them the proof or show them the working which I have just shown you. Thank you, students.